Chapter 3, Solving Problems by Searching. This is a relatively long chapter and we will focus on many search algorithms. We will start by discussing an interesting problem that we will refer to as the Romania problem. Say, for example, we have an agent, and the agent is in the city of Arad, Romania. And say the agent is enjoying a touring holiday. Um, Here's a picture of the city of Arad, a beautiful city. And here's a map that shows the city of Arad along with many other cities in the surrounding area. Here's Arad, Sibiu, Zerin, Timisoara, and so on. So to make things interesting, say for example the agent wants to improve its suntan while the agent is at Arad, improve its Romanian, enjoy nightlife and avoid hangovers. Most importantly, however, the agent has a non-refundable ticket to fly out of the city Bucharest in the following day. So here's your agent in the city of Arad, and the agent has a ticket to fly out of Bucharest the next day. In other words, no matter what the agent does, ultimately the agent has to reach Bucharest by next day to fly out of the city. So the goal is to reach Bucharest on time. In other words, we want the agent to travel from Arad to Bucharest, taking a shortest path possible through all of these possible cities to reach Bucharest on time so that the agent can catch the flight next day. To solve problems like those, we need to define them properly. We need to define both the problem and the solutions, or format it in a way where we can obtain solutions. And a problem can be such a problem, a search problem, can be formally defined by describing 5 components. The first component is to define initial state. That is, where does the agent start solving problem from? In our case, for the Romania problem, our initial state will be in Arad. So in Arad defines our initial state. This is where the agent will originally start. Our next component is a description of possible actions that is given an agent as in a particular state, or in general, what actions can the agent take. For example, if the current state for the agent is in Arad, then the applicable actions that the agent can take are these. The first action is go Sibiu. From Arad, the agent can go Sibiu. The second possible action is go Timisoara. And the third possible action is go Zerin. We also need to define a transition model. A transition model defines what happens at a given state after you take a particular action. So we define successor as any state reachable from a given state by a single action. So if you are at this city, let's say Reminishu, then the possible actions that you can take are either going to Sibiu or Pitse, Pitsti or Cravioa. So then the successor states are these 3 possible states, these 3 possible cities for the current city that you have. A transition model defines what happens when you're in a particular state and you take a particular action. In other words, here one example of a transition model is the result of being in Arad and going to Zerin is you will result in this new state of in Zerin. So if you are in Arad, You take this action of going to Zrin, then the resulting state will be that the agent is in Zrin. And the initial state, the actions, and the transition model define something known as the state space of the problem. We'll look at a specific example of how a state space looks like. But a state space in general is a set of all states reachable from the initial state by a sequence of actions. That's what's contained in a state space. A state space forms a directed network. So state space forms a directed network in which nodes are states and the links are actions. We will look at one example of how to build a state space or how a state space looks like. The next component is goal test. So what this component determines is whether a given state is a goal state or not. So for this, we will also need to define goal states. In our case, the goal state is simply the list of cities where we want the agent to be, which now only has one component, that is one element. So our goal states are this: in Bucharest is our goal state. And goal test is a mechanism which allows us to check whether the agent is at the goal state or not. The last component is to have a path cost function. That is a function that takes a path as input and gives you a numeric score that tells you how good or how bad the path is. So it assigns, we need a function that assigns a numeric cost to each path. So we've defined how a problem should be described or formulated, including the goals. How do we define optimal solution? Or in other words, how do we know that we have achieved the goals that we want? So let's start by describing what a solution is. Intuitively, you may think that since the problem is from going to Bucharest from Arad, the output of the algorithm at the end will be this city, Bucharest. But that's not true. What we are looking for in the algorithm, so output of the algorithm is action sequence. In other words, we want the algorithm to output the steps that the agent needs to take to reach Bucharest. So the solution that we are looking for is action sequence that leads from initial state to goal state. And the solution quality is measured by the path cost function, which is already described in our problem. Now, given an algorithm, let's say an algorithm is there that takes this problem as input and gives you a solution, right? It gives you a path or an action sequence that takes you from the initial state to goal state. Once again, we are not looking for an algorithm that gives you a solution, because there may be hundreds of thousands of solutions depending on the problem, and some solutions may be terrible. Instead, what we are looking for is an optimal solution. That is a solution that has lowest path cost. Because it is a search problem, we know that there are solutions. We are searching for a path that has lowest cost. So we are looking for the optimal solution among all solutions that may be possible. Now there are so many details in the actual world. For example, in case of the Romania problem, the agent may be traveling with companions, there may be scenery out of the window that the agent is watching, the conditions of the road, the weather, and so many things. We've simplified everything, and we've simply said something like the agent is currently in the state of Arad. We've intentionally left out all other considerations in the state description because they are irrelevant to the problem of finding a route to Bucharest. Now, you may intuitively say, well, weather is relevant, right? Because if the weather goes bad, then the time it takes or the algorithm that works to find shortest route may not work properly. But here's the catch. In designing the problem, let's say we had these cities. Here's your city of Arad. Here's Bucharest, right? There may be multiple paths to go from Arad to Bucharest. We assigned numbers between these cities. Now these numbers may not reflect the actual miles between these cities. Instead, they may represent the cost of going from city A to city X. So this can be cost. And this cost should incorporate everything that is needed to calculate the cost of going from A to X. So everything combined, conditions of the road, weather, and all of the things put together give you this cost of going from city A to city B. So now, once we have this cost, everything else becomes irrelevant because now we have sort of squeezed everything into this number. So this process of removing details from a representation to obtain mathematical formulations or to obtain a minimalistic way of formulating the problem is known as abstraction. Now, choosing the level of abstraction may depend on your problem, depend on your choice of what algorithms you have to solve the problem, and so on. So, how many details do you want to consider? Whether do you want to consider everything such as stopping in red light, looking out of window, and all of those? It's up to you when designing the problem formulation. Before we look into search algorithms, let's first look at some sample search problems. We already talked about the vacuum world problem. This is one search problem. In this slide, we will focus more on understanding the state space for the vacuum world problem. In other words, how does a state space look like? Say here's where our problem begins. This is your room A, room B, and here's your vacuum cleaner agent. And there's dirt in both rooms. The possible actions that the agent can take is going to left. That is, the agent is already in this left room and the agent is trying to go left again. If the agent tries to go left, nothing changes. In other words, the agent stays in the same state. Say instead, the agent takes the action of sucking this dirt in the current room where the agent is at. Then this action, represented by this line of sucking dirt, leads the agent to a different state. So if this was a state 1, now the agent will go to a state 2. In this state, we have still room A, room B, but now room A is clean because there is no dirt, but the vacuum cleaner agent is still in room A. And room B stayed the same. Instead of taking this action of sucking dirt, if the agent had decided to take a right instead, then the first room, room A, would still be dirty, but then the agent would be in room B, the next room. So that would be a third state, another state, because this is different from the previous state. So say the agent decided to suck the dirt and go to this state 2, then once again the agent has 3 choices, either going to left or going to right and reaching this state of state 4, or sucking the dirt and staying in the same room, because if the agent is in room A and it continues to suck dirt, then the agent will stay in the same room. So in this way, if we consider all possible scenarios, then we end up with these 8 states. So such a set of all the possible states for a problem represent the state space for the problem. Let's try to formulate the vacuum cleaner world problem. In other words, we want to define the 5 components that describe the problem. We will first start by defining what states possible are for the problem. A state is determined by both the agent location and dirt location. So we saw that the agent could be in either of the 2 rooms, or the dirt could be in either the 2 rooms. The agent is in one of the two locations, each of which might or might not contain dirt. In other words, the number of 8 possible states that we obtained is obtained using this formula, 2 times 2 to the power 2. In general, if we have n rooms, then this formula for calculating the possible states becomes n times 2 to the power n possible states. So if we had 4 rooms, then the number of states would be 4 times 2 to the power 4. So the first thing that we describe for the vacuum cleaner problem world is the initial state. Here, any state may be designated as a starting state. The possible actions that the agent can take are left, right, and suck. And the transition model is obvious. If the agent is, let's say, at the beginning in this state, and if the agent sucks the dirt, then the agent will reach to the next state, second state. Now, what's different about the transition model is that if the agent is in a certain state and the agent decides to take left, say for example from a state like this, then this has no action. If the agent is already in the state of already in the right room, and if the agent decides to move right, then once again this has no effect or no changes in the state. Similarly, if the agent is in a state where the room is already clean and the agent takes the action of sucking the dirt, then once again the agent stays in the same state. Now, goal test is simply checking whether all squares are clean or not. In other words, what we want is if both the squares are clean, then a state like this, then this will be our goal state. We can define the path cost as each step having a cost of 1. That is, each time the vacuum cleaner either sucks a dirt, moves left or moves right, or takes any action, then the cost is 1, so that we can obtain this goal state with minimum movements from the vacuum or minimum actions from the vacuum. So obviously, compared to the real world, this toy problem has discrete locations, discrete dirt, reliable cleaning, and it never gets any dirtier because we have abstracted the problem into something very simple. Another problem that we will look at is the 8 puzzle game. The 8 puzzle game is a problem that looks like this. You have 9 blocks total, actually 8 blocks, and 1 blank space. So here's your blank space in this case. And the goal is to move these blocks into these blank spaces repeatedly so that eventually we reorganize the blocks into something that looks like this. Say, for example, numbers ordered according to their sequence. So the problem is that we have a 3x3 board with 8 numbered tiles and a blank space. And a tile adjacent to a blank space can slide into the space. So here we can slide 6, 2, 5, or 3, any of them into the blank space, and we can repeat this over and over again. The objective is to reach a specified goal state, and in this case, the goal state will look something like this. Now, this problem can also be formulated with, let's say we want to build a picture, a really big picture that has blocks. The picture is broken down into blocks, and we want to assemble the pictures into the final picture that is expected. Here's an example of the 8 puzzle game with the blocks as pictures. Here is the solution with all the blocks solved. So let's create a problem. Here's the challenge with all the 8 blocks. This is here's the blank space with all the 8 blocks placed differently. Our objective is to rearrange these blocks so that we obtain the full picture. So let me try to solve this. For an 8 puzzle like this, let's see what the states are and the 5 components of defining the problem are. So the states are the location of 8 tiles and the blank in one of the 9 squares. The possible states that we have is approximately n factorial. Any state can be our initial state. Now the possible actions are moving either of the blocks to the blank space, but effectively we can imagine that the possible actions are actually the movement of the blank space. That is, whenever we move one block to the blank space, we're effectively moving the blank space to that block. So instead of thinking that we can move various blocks to the blank space, it is easier to imagine that we can move the blank space anywhere possible. So we can move the blank space up, down, left, or right, and those are our possible actions. Transition model is simpler. Given a state and action, it results in a resulting state. In our case, just simply the movement of blank space. Goal test is simply checking whether the current state matches the goal configuration. Here's our goal configuration. Configuration and state can be used interchangeably. The path cost is 1 for each step that we make. In other words, the more movements you make to obtain a solution, the higher cost associated with it. Let's look at some real-world problems as well. A category of problems known as route finding problems are common in the real world. Say, for example, a travel planning website wants to solve the air travel problem. The air travel problem is given a city where you are at, what route should you take to reach the destination city that you want to go to. Now the possible states are each state includes location and the current time. That is, where are you currently at? Your that is your location, and time. What time is it? Initial state is defined by the user's query. In other words, say for example, we are flying to city X from St. Louis, then our initial state will be in St. Louis and current time, whatever time it is. Actions is take any flight from current location in any seat class, leaving after current time, leaving enough time for within airport transfer if needed. That is, what we want is the output to be, let's say, in city X at time T. That's enough for you to catch the next flight so that you can reach the destination city. The transition model looks like this. So the state resulting from taking a flight will have the flight's destination number as the current location and the flight's arrival time as the current time. In other words, say for example, I would like to go from the city of St. Louis, I would like to go to city X, and from city X, I would like to go to city Y. And let's say the current time is, let's say, A. Then let's say the time that it takes from city X, from St. Louis to go to city X is, let's say, P. Then this current state of being in St. Louis and with current time of A and taking this action of going to city X will result in a new state where the agent will be in city X and the time will be A plus P, because this is what the time that it takes to go from St. Louis to city X. The goal test is simply, are we at the final destination specified by the user? And the path cost depends on many things like monetary cost, waiting time, flight time, customs, immigration, and so many other things. In other words, the problem here is you are in city A, you want to reach city B, you have a current specific time T, let's say you want to reach here by time, let's say T dash, and you have many other intermediate cities in the middle. So you have so many options of going through all of these cities and eventually reaching city B. What path should we take from city A to city B so that we have minimum monetary cost, waiting time, and all of these other parameters? Another sorts problem. Now, There are another class of search problems known as the Turing problems, which are slightly different from the root finding problem. Here's a map of the St. Louis Zoo. Here's our south entrance. Here's the north entrance. Here's our snake house. Here's the train track, and so on. An example of a Turing problem is, say for example, an agent wants to visit every species of animals at the St. Louis Zoo at least once, starting and ending at the snake house near the south entrance. So this is where we would like to start. And we want to visit every possible species of animals at the zoo, and then come back to the snake house. Problems like these are known as Turing problems. Although this may look like very similar to root finding problems, these are different. The state space is different for Turing problems. To correctly represent a state space, each state must include not just the current location, which is sufficient for root finding problems, but here it must also include a set of cities that the agent has already visited. In other words, the agent's initial state would be something like in snake house, visited snake house. And a typical intermediate state would be something like in giraffe house, visited snake house, primate house, giraffe house. One single state will need to contain the information about where the agent is, also what states the agent has visited. The goal test is also different. The goal test is not to check whether we are finally at the snake house. Instead, the goal test is to check whether we are at the snake house and whether all animals have been visited or not. Let's look at some additional real-world problems. One very popular problem is the traveling salesman problem. The traveling salesman problem is that, let's say we have a traveling salesman who's trying to sell certain items. The salesman wants to visit each city exactly once. The aim is to find a shortest tour. That is, how can the traveling salesman visit all the cities that he wants to visit exactly once, come back to the original city with the shortest tour possible. Another problem is the VLSI layout problem. Here's a picture of a chip that's in many of the today's electronics. Say, for example, this could be the motherboard in your laptop, or your motherboard in your cell phone, and so on. So such a motherboard or a plate that has many transistors and capacitors and many other components, CPUs and many other things, have connections between them. Say, for example, this may be your first transistor, T1, this may be another component, C2, and you may need to connect them, maybe have 20 different wires that connect these two components. The challenge here is, how do we place these components into a board like this such that we want to have minimum area of the entire board, we have minimum circuit delays so that the components don't have to wait for each other very long, and maximize manufacturing yield. The cost of laying out copper and gold and many other components within the plate may be very high. So how can we place components in such a board to optimize area, circuit delays, and many other things? That's another search problem. The next problem is robot navigation. So far, the route finding problem that we saw are 2D problems. So given this map, we want to find shortest path between A and B. Robot navigations are more complicated versions of that problem. A robot can move in a continuous space, that is any place in the 3D, and the robot has arms, legs, and wheels. That makes the problem many dimensional, because now we have to determine where or what is the shortest path for each component or each possible movements that the robot can make with its components. Another such problem is automatic assembly sequencing. The aim is to find the order in which to assemble the parts of certain objects. Say, for example, if some people are assembling a car, then what should we do first and what should we do second so that we can obtain the final product in a smallest possible time, shortest possible time. Here's a question. Out of these, which are Turing problems and which are root finding problems?